All right, so today I had already talked about the series expansion for, various different functions. And one of the functions that I talked about briefly was x raised to x. Now, recently, when I was browsing the internet, I saw an interesting question, which is to integrate from 0 to 1 x raised to x dx. What is it going to be? Now, this question, as someone who likes, series expansion and stuff like this question, it was really interesting to me because, you use series expansion to solve this. But I'll give you a little bit of a spoilers here. Now, as they proceeded with the solution, what they used was, I think, the gamma function. But as someone who doesn't know much of gamma function, we're going to proceed with it, a bit more medievally, I'd say, by pure logic. Okay, so let's see how you can tackle this by just knowing series expansion and basic integration, and just, I guess, a bit of logic. So, as we all know, the series for x raised to x is 1 plus x log x divided by 1 factorial. If you don't know what I'm talking about here, you can refer to my previous videos where I discussed the series. So here we get this, right? All you have to do is just plug this in. So integrating from 0 to 1, 1 plus x log x by 1 factorial plus x log x squared by 2 factorial, so on and so forth. So you can actually express this in the form of a sigma notation. Now, I don't know much about calculus, I tell you that much. Now, apparently, I think there is some things that you have to prove first before you have to exchange the sigma function and the integral function. I don't know none of that, okay? But thankfully it worked out here. If someone does know what it is, please educate me in the comment section, or maybe I'll look it up on my own sometime later. Anyway, you can write this as generally, x log x the whole raised to n divided by n factorial from n. The sigma, it varies from n is equal to 0 up to infinity, right? It's an infinite series. Now, this whole thing with respect to dx, we need to integrate it. So I'm going to just interchange this. Sigma n equal to 0 to infinity, integral 0 to 1 x log x the whole raised to n divided by n factorial dx. This is what we have. Now, how do we tackle this monster right here? Well, I think this is where they use the gamma function, but let's just proceed by pure logic here. Okay, so I'm just gonna write this thing right here, this bad boy. Let me refer to him as some I dash. This guy, let me give him as some I. So let me evaluate I dash real quick, and I'll be right back. So I dash is integral 0 to 1 x log x the whole raised to n divided by n factorial dx. Now, with respect to x, n is a constant, right? So here, what we did is n is only varying for the summation. It's not varying for this this integral. It's a constant for this integral. So we can just move this outside. This guy is not going to cause us any problems. This n factorial just goes outside. Now, we have integral 0 to 1 x log x the whole raised to n dx. How do we deal with this guy? Integration by parts. Okay, so let me try to do this. So I don't know the integral for log x for higher powers, so I'm going to take that as the second function. So we know that by integration by parts, I can write this as, right, x raised to n into log x the whole raised to n, right? So I'm going to take this as the second function, this is the first function. So I'm going to write this as, oh, sorry, this is the first function, and this is the second function. Because, you know, when you do integration by parts, you'll do first function into integral of second minus integral of derivative of first into integral of second. It'll be much better when I write it down, okay? It's much more confusing when I say it. So I'll write it down as log x. This I'd say it was much better to call this as I dash. Anyway, I double dash. Let me evaluate it separately. This thing you can write as log x the whole raised to n, that's the first function, into integral of second, x raised to n's integral is x raised to n plus 1 divided by n plus 1, minus integral of what is the derivative of the first, that is, you need to use the chain rule here, right? N log x raised to n minus 1 divided by what is the derivative of log x is going to be equal to x. That times x raised to n plus 1 divided by n plus 1 dx. Right? So here you have x raised to n plus 1 log x raised to n divided by n plus 1 minus here you will have the n is a constant, so you can put that outside. N plus 1 is another constant, you can put that outside. This x and this n plus 1's x can also get cancelled. So what do you get? Here you have integral x raised to n log x the whole raised to n minus 1 dx. Now, the astute observers will realize that this x raised to n is staying the same here. Meanwhile, the log x is reducing in power. Now that's a good thing for us because, well, the thing that is causing us issue was log x, right? So now the log x thing's powers is decreasing, so we can finally, you know, get a properly integrable function. Basically, all we need to discover is that there is a pattern in this entire thing. So the first thing, it was x raised to n plus 1 log x the whole raised to n divided by n plus 1. Then the next thing became n divided by n plus 1 times this thing is the same as this thing, but instead of n here, it was n plus 1 here. Sorry, n minus 1 here. That's the only difference. So here it will be log x raised to n minus 1 there, and will be x raised to n. This part will be the same. This part will be the one that's different, right? Log x raised to n minus 1 will be here. So you'll get log x raised to n minus 1, x raised to n plus 1 divided by n plus 1, minus n minus 1, log x raised to n minus 1 minus 1 is n minus 2, divided by x, and x raised to n plus 1 divided by n plus 1 is there. So n divided by n plus 1, that thing is always going to be there. So this into what will be here is that this thing, like I said, is going to be the same, except the log x the whole raised to n minus 1 part. X raised to n plus 1 divided by n plus 1 is going to be there. That is going to be the first part. The second thing is this thing right over here, which is minus n divided by n plus 1. Sorry, not n divided by n plus 1. This will be n minus 1, right? N minus 1. Divided by n plus 1 is going to be the same. But here, like I said, instead of this, the derivative of this, okay, I need to explain this further. See, this is going to be your first function in the second time you integrate this. And the derivative of this thing is going to be n minus 1 log x raised to n minus 2 divided by x, right? So that n minus 1 is going to be here, and that's what I've written here. And what you'll get is n minus 1 divided by n plus 1 times integral. The x raised to n is going to be remaining the same, and this will be log x raised to n minus 2 dx, right? So you see the pattern here? This thing, there'll be n divided by n plus 1. Here will be, so alternating plus and minuses. That's the first thing that you observe with these terms. The next thing is that this becomes n minus 1. The next time it becomes n minus 2 here, the numerator. The denominator, the n plus 1, is going to be the same. Then also the log x, thing is going to decrease. So if I were to write I double dash, it will be kind of like this: x raised to n plus 1 into log x raised to n divided by n plus 1. That's the first one. Then n divided by n plus 1 times x raised to n plus 1 divided by n plus 1 times log x the whole raised to n minus 1, right? That is what we got from here. And the next term is going to be a plus, and it's going to be minus and minus is plus, n into n minus 1 divided by, there will be an n plus 1 here, there will be an n plus 1 here, there's going to be another n plus 1 when you further integrate it from here. So you can just observe it, right? Here you had here you had 1 n plus 1. Here you had 2 n plus 1s. Here you have 3 n plus 1s. Like this. And you will have x raised to n plus 1 is going to be the same. And log x will be log x raised to n minus 2. Okay?